So these are the three structure changes during the creep formation: deformation by slip, subgrain formation, and grain boundary sliding. Okay, so the next one is the mechanism of creep deformation. So what happened inside the material, how this at elevated temperature and constant load with respect to time, how this deformation happen inside the material. So that is explaining the mechanism of creep deformation. Okay, and basically the creep deformation for creep mechanism is not a single mechanism. Okay, it is a collection of different mechanisms like a cross slip and a climb. We already studied this cross slip and climb in the second module, and diffusion, grain boundary sliding. So these are the four mechanisms which is the main reason for this type of creep deformation or creep mechanism. Okay, and out of this cross slip and climb. Okay, so out of this, the cross slip and climb is dislocation based mechanism. We already familiar what is cross slip and climb, and the second one, the diffusion and grain boundary sliding. So that is not based on the dislocation mechanism. So this four mechanism is the mechanism of creep deformation. So we already discussed this cross slip and climb. In case of cross slip of a screw dislocation, we can see two slip planes here. So this is a slip plane one. This one is the slip plane one, and the slanting one is the slip plane two. Okay, and here this is a one screw dislocation, and the Burgess vector of the screw dislocation is along this line, and the movement of screw dislocation is in this direction. Okay, so the screw dislocation is moving in this direction, and when this screw dislocation reach this point, this one. Okay, so this is my screw dislocation, this one is my screw dislocation, and it is moving in this direction towards this precipitate or obstacle, and when it reaches this point, okay, this obstacle actually prevent the forward motion of this dislocation. Okay, it cannot move further forward by the restriction offered by this precipitate. Okay, so it cannot move. So what happened? This dislocation further move from slip plane one. This is my slip plane one, and this is my slip plane two. This is my slip plane two. Okay, so the movement of the screw dislocation in this direction along the slip plane one is restricted by this obstacle. Okay, so this dislocation cannot move further along the slip plane one. So what they do, the dislocation move along the slip plane two. So it's changed the direction from slip plane one to slip plane two. So the dislocations move from slip plane one to slip plane two. So this is the further motion of the dislocation. So this process is called cross slip. Okay, so this cross slip is the first mechanism for this creep deformation. Okay, cross slip. And second one is already I explained the climbing up and down of these dislocations. When it moves in this direction, the precipitate offer restrictions for the movement of this edge dislocation. Then what they do? They under high temperature, these atoms has higher energy. So the higher energy atoms climb up or climb down to overcome this precipitate restriction. Okay, so these atoms in around this precipitate climb up or climb down. They have enough energy for this climb up and climb down because the creep is actually occurring at a very high temperature. So atom has very higher energy for the diffusion. So they diffuse into upper region or bottom region by climb up or climb down process. Okay, so thereby climbing up is another mechanism of this creep deformation. And third one is diffusion. Diffusion is the third deformation mechanism. In case of diffusion, actually what happened is that, so this is my a grain. Okay, in this grain, I am applying a tensile load here. a constant tensile load is applied here. So in this tensile load, we can see two types of grain arrangement. So one type of grain arrangement is this one, the grains which is parallel to the direction of stress. Okay, these are the grains which are parallel to the, which are arranged in the direction of stress. Another set of grains is this one, the grains which are perpendicular to the direction of stress. Okay, so when during this creep formation, creep deformation, these all the grains, all the atoms are under very high temperature. So there is a chance for diffusion. Okay, so when we increase the temperature, the driving force for the diffusion also will increase, and there is the probability of diffusion will increase by the increase of temperature. So during the creep formation or creep deformation, when we apply the stress, what happens is that there will be movement of these atoms from this area. That means the atoms in the direction of stress from this position to this position. So atom will move in this direction. Okay, atoms will move in this direction. Similarly, here also the atoms move in this direction. Okay, and when these atoms move in this direction, similarly in this direction also, to the bottom also. Okay, some atoms move in the bottom direction and some atom to the top area. Okay, so the atoms will move by means of diffusion at a elevated temperature, and this is a substitution diffusion process. Okay, and this diffusion process is assisted by the stress. This is a stress assisted diffusion process, and as well as the vacancy assisted diffusion process. How this diffusion happen? For example, in this top layer, we have one vacancy and 4 atoms. So this this point is vacant. So one atom from this point move to this vacancy, and the amount of vacancy concentration is very high at a very high at a elevated temperature, because elevated temperature, under elevated temperature, atom has more energy. So there is a chance for the movement of atoms from regular lattice position to interstitial or substitutional position. So there is a chance for the creation of vacancy in this grain at elevated temperature. So the number of vacancies presence will be very high at elevated temperature. So the atoms from this position, which is parallel to the applied stress, move from this point to the vacancy position. Okay, so when the atom move from this point to this point, here a vacancy is created. So the vacancy movement will be like this: vacancy movement in this opposite direction, and the atom movement in this direction. Okay, so atoms or vacancy migrates from grain boundary. So these are the grain boundary. The atoms occupied in the grain boundary region. All the atoms are, we only consider the atoms which is in the grain boundary region. Okay, so vacancy or atoms migrate from the grain boundary which are perpendicular to the stress. So in case of vacancy, the vacancy move from the area of perpendicular to the stress direction. It is moved from the perpendicular to the stress direction to parallel to the stress direction, vacancy movement. But in case of atom movement, atom move from the parallel position to perpendicular position. Okay, so such type of diffusion is another reason for this creep deformation. So by this diffusion, what happened? The atoms in this position move to this position. Okay, so finally what happened? Finally, this will be the shape after such type of diffusion. The length will increase and the diameter will decrease, because atoms in this diameter area is moved to this in this area. So the length is increased and the diameter is decreased. Okay, so such type of diffusion is the another mechanism for creep deformation. And the fourth mechanism is grain boundary sliding. I already explained what is grain boundary sliding. So initially it is a straight line. After grain boundary sliding, we can see this is a discontinuous line. So there are some sliding motion of the grain 2 with respect to grain 3. Okay, so that is the 4 mechanism for the creep deformation. Okay, And the last topic is this, based on this mechanism, we can plot a map. In this map, we have the y-axis is stress by Young's modulus. So that is actually eliminate these units. We use divide by E term, and here T by Tm, temperature divided by melting point. So by plotting this graph, this is my yield point, sigma y by E. So above this yield point, there is no such a creep deformation. The dislocation will be a sliding, gliding dislocation motion. But below sigma y, the deformation will be because of creep at elevated temperature. Okay, so here we can see there are three regions in this region, in this map. And this region is elastic region. This one is a dislocation climb region, and this is a diffusion region. Okay, out of these four mechanisms, dislocation climb and these diffusions are the main mechanism for creep deformation. Okay, so which is plotted in this graph, in this map, and we can see when the temperature is very low, when temperature is low and the stress applied is low, the deformation will be elastic. But when we increase the temperature, at a higher temperature and higher stress value, the mechanism will be climb up or climb down mechanism for creep deformation. Okay, there is no chance for the diffusion mechanism for creep deformation. So at a elevated temperature, higher temperature and a higher stress value, the mechanism will be climb mechanism or dislocation climb mechanism for creep deformation. But for under higher temperature and a lower stress value, we can see this region is associated with the lower stress value. So under lower stress value and a higher temperature, diffusion mechanism is the significant mechanism for the creep deformation. Okay, so this graph showing, the map is showing the different mechanism associated with the creep deformation under different temperature and stress values. Okay. And this is the threshold for creep. We know the at least 50%, 40% or 50% of the temperature is required. 50% of the melting point temperature is required for creep deformation. That is a critical temperature for creep deformation. And other than this, stress applied also is an important factor for creep deformation. There is a threshold value of temperature and a stress value for a creep deformation. So when we apply or increase the temperature above this threshold temperature and threshold stress value, then only the creep deformation appear in the structure member. Okay, so that is about the threshold value of creep. And there are different methods for the prevention of creep. The one method is high thermal stability. For a particular material, if you take a material with a high thermal stability and a high melting point, okay, then we can reduce the creep deformation or creep mechanism. Reduce here. Okay, so for example, in case of tungsten, it has very high melting point. So even at a room temperature, it will not affect any type of creep deformation. But in case of lead tin alloy, it has very low temperature, melting temperature. So under room temperature, even under room temperature also, it may subject to creep deformation. So we have to select a material with a high thermal stability. Another methods are precipitation hardening. We already discussed what is precipitation hardening. Different types of impurities are added to the material and which prevent the creep resistance or creep deformation will prevent by this precipitation hardening. Again, dissipation hardening also, when we add the material, impurity material, that may disperse in the matrix of the parent material, that is also improve the creep resistance. Cold working and hot working, thereby strain hardening can be increased. Strain hardening also improve the creep resistance. Okay, and substitution solid solution, alloying, that is the alloying. Okay, alloying also increase the creep resistance of the material. Okay, so these are the different methods. Stainless steel, refractory metals, supralloys. We will discuss about supralloys later. So these are very good materials under very high temperature atmosphere. They have high creep resistance even at a elevated temperature. Okay, so we can use this type of material where temperature is very high, subject to creep deformation. Okay, and single material and highly elongated grain materials show very high heat creep resistance than that of this polycrystalline material. Okay, so in case of these three turbine blades, this is a conventional cast turbine blade showing less creep resistance, and columnar grains show good creep resistance, as well as single crystal also showing good creep resistance. Okay, so by using such materials or design consideration, we can improve the creep resistance. Okay, so that is about this effect of different factors about the, or how can we prevent this creep by this solution formation or hardening methods or cold working methods, etc. Okay, so that is about the prevention methods. Any doubt in this?